In order to understand the reasons, you have to understand some evolutionary biology. It's evolutionary biology that tells you why is it that HIV is so difficult to cure. For one thing, the virus, which you're seeing over here, attacking a human cell, that's a human lymphocyte cell, a human defense immune system cell. The virus mutates very rapidly. Mutations are one of the two fundamental components of evolution. Evolution works with two fundamental processes. One is mutation, which is random, and the other one is natural selection, which is not random. Well, mutations in the HIV virus occur very rapidly, which is one of the reasons that it's very difficult to find a cure. Because it literally mutates under your very nose, since it has a very rapid lifestyle. The other one is the environment. The environment of an HIV virus is very complex because it depends on the sexual behavior of individuals, which are very complex and varied across the world. And in fact, they are so varied that there are different kinds of HIV virus that are adapted to exploit one kind of sexual behavior or another. All of this is perfectly understandable in terms of evolution. What you're looking at from the 1940s on is the evolution of a new form of virus and how it spreads through populations and adapts to new conditions. This is exactly what evolutionary biology would predict. Now, what about the idea of evolution as descent with modification, which was Darwin's original definition of evolution? So that's what he meant. He wasn't aware of this particular kind of diagram, but this is a diagram of the evolution of the ceratopsians. The ceratopsians are the three-horned dinosaurs, which are very common in museums, in paleontological museums all over the world. That's what we know right now, as of now, of the evolution of ceratopsians. These are the different forms and how they are related to each other. You can see, incidentally, that there are a lot of intermediate forms, which is another one of the myths of creation, that the intermediate forms are not there. Well, evolution is descent with modification, that is, as this kind of diagram that I'm showing here. It started by a variety of disciplines, including comparative anatomy and paleontology. And the evidence for this evolution by descent comes from a variety of disciplines, from organisms and morphology, for the study of the physiology of those organisms, from the developmental biology of those organisms. All these different pieces of information, which of course I don't have time to give you into any detail at this point, will fit very well with each other, and they represent the general evolutionary explanation of how life actually emerges. There's also, of course, evidence from the fossil record, and what you're looking at here is the evidence from the fossil record, or it's part of the evidence from the fossil record. I'll show you a few other pieces of evidence from the fossil record in a minute. But this is what evolutionary biologists mean by descent from by modification. Let me give a specific example, like in the case of the HIV virus for molecular evolution. Let me give you a specific example in the case of descent and modification. One of the best known examples of descent and modification that we have come to understand in the last few years is the evolution of whales, which is sort of summarized over here. These are the actual skeletons that have been found in the fossil record. These are the actual currently living whales. There are two major kinds of whales, the sperm whales and the white whales. It's over here. So the baleen whales are one kind, and the toothed whales are the other kind. These are some of the intermediate in the fossil record, and this is a reconstruction of what these might have looked like. Well, how do we know? Because we have a bunch of the intermediates. Of course, we don't have the actual animals, so this picture that he's looking at you is not what we have. What we have is the skeleton of that fixed creature. The evolution of whales started about 55 million years ago with some animals of this kind, which are called mesomytids. These were hyena-like creatures. They were scavengers and fish hunters. And if you want to find something today that essentially has the same ecological niche, you would have to look no further than bears. Bears have actually a habit and way of living that's pretty similar to what the mesomytids would have had 55 million years ago. Then there is a large number of intermediate forms which have always been discovered in the last few years. Until a few years ago, I wouldn't have been able to tell you the story about the evolution of whales because we didn't know anything about the evolution of whales. 53 million years ago, it is only a couple of million years after the animal that I just showed you, and that's nothing in geological terms. It's a blink of an eye. Another animal appeared called Hamalayacetus. It lived in fresh water and the sea. If you wait another 3 million years, you have Pachycetus, which lived on both land and water. And then you have this guy over here, Ambulocetus, which appeared between 45 and 50 million years ago. It had very reduced limbs, and you can see already that it looks much more similar to what today is our marine mammals than to the animal that I showed you a minute ago. In fact, it looks pretty much, and it has the same kind of habit, it had probably the same kind of habit, the same kind of lifestyle, as say a sea lion. So if you want to see what an intermediate form will look like actually today, those capabilities do. We look at these kind of animals live. Of course, I'm not saying that a sea lion is an intermediate between whales and whale ancestors, but it looks like what an intermediate would have been. A little later on, 35 to 40 million years ago, we have this fellow, Basilosaurus, and a variety of other species of which we have found the fossils. And this thing really has extremely reduced limbs, and it really had a completely marine habit. We know that because it's found only in sediments that accumulate under marine conditions, not under fresh water. So, we actually know from combining these two kinds of information, the fossil information about evolution by whales by the sand, and the molecular biology of whales, that in fact whales are fairly closely related to hippos, which are these animals that we're showing you here. There's the hippo and there's the whale. They're very closely related, meaning that they share a common ancestor, last common